Yes, great.
Okay, thank you very much for having me, Alexandra and Laius, for this presentation. And I have to say that I think the sort of outline of my talk is going to mimic that of Jorge's in terms of like how I'm going to discuss this application area. So maybe discrete optimizers speak somewhat similarly. So this has an overtone from a mechanical engineering perspective. I'm in the mechanical engineering department at the School of Mines. And so this work we've been doing on concentrated solar power is definitely a very mechanical topic. And with that, I want to thank my collaborators. This is sort of a subset of everyone who's been working on this project who is in some way connected. These here, Mike Wagner is a former PhD student of mine who's now in the mechanical engineering department, not surprisingly, at UW-Madison. And so he's the person who first brought this problem to our attention. And I also have to thank him for enjoying having operations researchers around. Sometimes it's difficult to work cross collaboratively. And so he was very good in, trying to say, well, we need some more rigorous math behind this. We've been fortunate to have two very good PhD students, both from the United States Air Force. So Lieutenant Colonel Jesse Wales, he's now a professor at the Air Force Institute of Technology. He did some of this work, and then he was followed by our current student, John Cox, a major in the Air Force, who will be graduating at the end of the summer. And then we also have two researchers from the National Renewable Energy Lab, William Hamilton, who got his PhD with me at the School of Mines and Mechanical Engineering, and Alex Zolan, who received his in operations research and industrial engineering at UT Austin. So they're both colleagues now at the National Renewable Energy Lab in Golden. So with that, I'll start talking about this type of solar power that no one knows about. And so this is not photovoltaics. This is very large scale. So on the order of hundreds of megawatts of power that's generated far, far away from you. And so the salient feature of the design that we are looking at is that there's a power tower. So a large tower that's surrounded by a field of these so-called heliostats or mirrors. And so the mirrors track the sunlight and they reflect the light onto the tower. And at that point, then there's actually this whole mechanical engineering system, shall we say, that sends the hot liquid down to a hot salt tank. So this is molten salt. So those of you who are familiar with your table salt, well, it is no more. It looks like water in this case here. It goes into a steam generation cycle. Part of that can go back to this cold storage tank, which is at a mere 288 degrees Celsius, as opposed to the hot one, which is over 1,000 degrees, or sorry, over 500 degrees Celsius or over 1,000 Fahrenheit. And so then the cycle continues. You might say, what on earth is the salt doing? That's the storage medium. So this is much more efficient than batteries. And so, I mean, batteries are chemistry, right? And so this is chemistry. It's just sort of chemistry in a very liquid medium without a lot of wires and so on. Anyway, so then, of course, this energy can be used if it goes through this sort of Rankine cycle here in order to generate power that's sent to the grid and so on. Right, so it's a very large scale endeavor. And in case this looks a little too abstract for you, I want to let you guys know we have one here in the United States. So here we go. This is in Tonopah, Nevada, which you've probably not heard of. It is about halfway between Reno and Vegas in Nevada. There's lots of things in Nevada, including Area 51. So here goes something else that you probably didn't know about. So you see the power tower there in the middle, and all the steam generation system and so forth surrounding it. And then you will see here all the little heliostats. And in this particular field, there's over 10,000 of them. And they're sort of arranged concentrically, and they'll track the sun. So I have a note at the bottom here. This has been on and off functional since it first came to be in 2016. It's got a very storied career. It's functional now, more or less. There's been a lot of issue. This is a mechanical engineering situation with the parts. So I mentioned that we had molten salt cycling through. Well, most of the heat exchangers and like the evaporator, superheater, preheater, reheater, all those components, they're used to having water and steam go through them. And now all of a sudden it's like, well, we're going to put salt through you guys. And then, people thought this would just be fine and there'd be no problems, but no one really did simulations to figure out that there might be problems. So that's been some of the issue with this, not so much the operations research or the system optimization associated with the, with the power tower technology, but rather just the way that the moving parts function. And that will come up when we look at the objective function and what makes a particular dispatch strategy better or worse. Right? But so this is the main one we have here. Some people might have seen something similar to this down in Southern California. And that would be Ivanpah as opposed to Tonopah. They have 3 towers, but they don't have any storage. So there's no dispatch and everything goes immediately to the grid. And they sell a lot to Southern California and Edison. So that we do have other such technologies, but this is the main one we have with the solar power and the molten salt. So, all right, so here we go. And this whole system on the left-hand side is what we've already discussed here with the power tower. And then on the right-hand side, you can also couple this with your more conventional photovoltaics with battery storage. And so sometimes we want to look at that as well. And we've done a little bit of work on that too. So I just bring this picture up because you see here, one of my students did a really good job of outlining in particular colors, different aspects of the whole system. And so what you can do is you can look at the design, and I'll talk a little bit now about the design, but then I'll focus more on the dispatch. But we've looked a bit at, well, how do you figure out like maybe how tall the tower should be, or how many heliostats you should have in the field, or what the ratio should be of the output of the receiver relative to its storage. It's called the solar multiple. And then various sort of electrical engineering things about power conversion, or how large the battery should be and so on. So these are some of the design characteristics that we've looked at. And unfortunately, that's an implicit model, but I'll talk just a little bit about that before I talk about the explicit dispatch, which is also not easy. All right, so this is mainly work with John Cox and William Hamilton, and they've been looking at this, it's a hybrid optimization performance platform framework. So this is something they've been developing, inside the National Renewable Energy Lab. And on the left-hand side, you sort of see a macro view of what they've done, the concentrated solar power with thermal energy storage, the photovoltaics and the battery, and looking at within the so-called system advisory model, which is a piece of simulation software that looks at the fluxes and all these very mechanical engineering style aspects of the system. It sort of evaluates, if you give it a design, what is kind of the utility of that design in terms of the power output and the amount you could possibly sell, and what you might have to pay in costs for parasitics and operations and maintenance. And so that design is actually hooked to this dispatch I'll talk about in a minute here. And there's kind of this back and forth with evaluating a dispatch relative to a design to try and figure out like the best design. But as you might imagine, there's very few variables in this type of model. I mean, we can only vary a few things at a time because the evaluations are extremely expensive. And like I say, they're black box. So we've been doing a little bit of work in that sphere, not because we can influence Tonopah, that plant's already been built, but there's been some international interest in, for example, parts of Northern Africa, as well as other places in the world, South Africa, China, Australia, Spain, these are Chile, Northern Chile and the Atacama Desert. These are all places that really lend themselves to this type of concentrated solar power, so desert atmosphere. And so then the right-hand side is just a little bit of sort of a schematic of how the gray on the left-hand side works, so that the gray inset there. So what we can kind of see from some of this is if you look at the design, you actually can be much better off than you might think otherwise, or than people did, for example, when they built the Tonopah plant. So nobody was really into optimization at that point. And so nobody thought about, well, what should we do? It was also difficult to characterize what various designs would yield in terms of operations and maintenance costs, or even profits and so forth. And so now that we sort of have a benchmark, we can say, well, things could be a little bit better. And so for various pricing strategies, the Pacific Gas and Electric in Northern California, sort of in the Bay Area, and then these pool price, two-tier, and then the California Independent System Operator. Just looking at a few of the different pricing strategies, you can see that if you're looking at this black box optimization in which you want to sort of minimize flux, or kind of what you're putting on the receiver that's going to stress it, and you want to also minimize costs associated with running your plant, for all of the pricing schemes, looking, at this sort of black box optimization, you can do quite a bit better in terms of the purchase power agreement price and in terms of the maximum flux. All those negatives are improvements because we're trying to minimize. So we want our purchase power agreement price to be lower because then we're more competitive in the market. And we want the flux to be lower because then from a mechanical engineering perspective, we are treating the system, the metal and so on, better. So then the overall objective, when we kind of looked at this by criteria optimization problem, was a reduction between about 15 and 20%, depending on the pricing structure we're looking at. So that's kind of a really high level overview to the design problem. And so what we'd like to do now is sort of take that design as fixed and go into the dispatch. And so now we're back in a more comfortable sphere, at least for me. So this is an explicit, I emphasize, mixed integer. In the first instance, we had a linear program. It was going to maximize the revenue generated from this electricity sales. But of course, we have other components in the objective. There's kind of 10 or 15 different terms, because not only do we have to take into consideration how much we can sell for, which is given by contract. So that wasn't something that we were optimizing. So we were looking at that, but then the parasitics are used to run the plant. So whenever we decide we're going to, dispatch power and correspondingly get the power from the field a certain way, we use some of our power to run all the generators and everything. So those are the parasitics, and we lose some in that. And then, of course, just from the general kind of operations and maintenance standpoint, the startups and the cycles into standby and so forth will cast some wear and tear on the system. And we were lucky enough that we could find, Alex Zolan was super helpful in this regard. He had done work with Dave Morton for his PhD, looking at the nuclear sector. And so there is a report out of Idaho National Labs that was able to get us a lot of the information on how badly the cycling would affect the system. So we were able to take that from a different system and use it in the solar power tower. And that was important because this technology is so new. We don't have a lot of, 10, 20 years down the road, how is all this wear and tear really affected your system? So all those parameters went into the objective as well. So then we had quite a few constraints. I'm not going to show all the math here, but I have oodles of papers that I'm happy to furnish people with. So we essentially have sets of constraints for the receiver. And then that was the heliostats in the tower you saw. And so obviously there's constraints on the startup and supplies and demands, the capacities, the logic governing the mode at which you're in. Like you can't be in standby if you haven't been running beforehand, or you can't shut down if you haven't been on for a certain amount of time, those kinds of things. And we have analogous considerations, again, all linear constraints for the cycle, the power cycle, that Rankine cycle you saw a little bit to the right of the heliostat field. So I want to bring your attention just to a single constraint. My convention here is I've got capitals for the parameters and lowercase for the variables. And so I'll just sort of read off to you what the constraint says, but it's essentially looking at the inventory balance. And so what we're looking at is like, how much do we have in storage? Like how much in that storage tank? And so what we have storage in time t is what we had in t-1 plus some conversion from power to energy. And then that's just a function of what we've been generating at the receiver, the XR, less the heat that's been emitted for various things. So the Qs are all heats. That's a common mechanical convention. And then also the XT would be from the power cycle, the generation from the power cycle. So that's kind of a simple kind of balance of flow, inventory balance constraint. We saw those in Jorge's model as well. And you notice that while the Ys are binary, the storage and the power generation are continuous. Okay. So what we did is we had various metrics of interest we were looking at for this sort of longer term model at hourly fidelity. We looked at sort of a year, a representative year. And so we looked at kind of rules of thumb that people would use to dispatch versus what our model would give. And we see that we're actually, we have a little bit less on sales and a little bit less correspondingly of the net electricity output. So you might think, well, that's not very optimized. But what you notice that we have huge improvements in terms of the way in which you're running the system. So all the wear and tear caused by the turbine starts and cycles, we've really been able to mitigate by trying not to shut it down and then restart it, just to capture that last little ray of sun at the end of the day, for example, if there's been a cloudy period. And so where we really gain in this model is, and where you gain a lot of times in optimization models, which is not just doing the greedy intuitive thing, which is how do I get more money? It's always looking at the trade-off between, well, you get more money, but it's at a price. And are you willing to pay that price to get the revenue? And so we contend that, for our particular example here, 1.5% decrease in sales is definitely more than offset by the gains we get in not having to do all that maintenance on the system. And so that's available with the details there. And at the bottom, I have a little bit about the system, the size of the system and so forth. So that was sort of one chapter. And then we moved along to the next chapter. So we have this little cartoon again, and it's coming back at you. It's not because I forgot that I already showed it to you. It's because, I just said we had this energy balance, and you guys probably noticed I had an S sub T, and that was the energy, and it was the energy at time T, but the energy isn't just in one tank. We had, for the astute observer, 2 tanks, a hot and a cold. And so if we really want to look at real-time dispatch instead of just, all right, let's dispatch optimally, see what we can do generally speaking, to get a view of the system at, an annual kind of horizon, we actually have to be much more discriminating in how we're modeling what's going on in the system. And so how we want to model this is the dispatch we want to put in 5-minute increments. And so now for people who are familiar with energy markets, you might say, yeah, that's a little bit more what you're going to have to do to play into those energy markets. So first hour at 5-minute fidelity, and then the next 3 hours at 15-minute fidelity. So where those 15-minute fidelity, you're not going to dispatch at that fidelity, you're going to dispatch at the 5 minutes, but at least it informs what's going on. And then for the next 20 hours of the day, we're going to just do hourly fidelity again. We usually have a 48-hour look ahead. That's standard in these kind of like market models. And so we have a model transition. And we'll talk about that transition later. But we're doing something different in the first day than in the second day, not just with respect to the finer time fidelity, but also with respect to some of the math. All right, so now we need our picture. So John Cox put together this extremely famous picture, and it will appear in a museum someday, I'm sure. So up at the top, we have the hot and cold tanks, and everything just mixed together, and we just got storage, and it's all just kind of in there. And so that was nice because it was linear. But you want to know, right, that's not the real world. The real world is often non-linear. So in the real-time model, we decided to take this fidelity to separate out what's going on in the hot and cold storage tanks. So the TES, again, that's thermal energy storage. And so now instead of just some sort of energy balance and that generation being the X, now we have in lowercase letters a mass flow rate of the receiver for the hot storage and the mass flow rate at the cold storage, and also the temperatures at the inlets and outlets. And so this is going to yield a much more complicated model. All right, so I got a little bit of notation here. I mean, the M's are masses, are mass flow rates, and the dot denotes the rate, standard in mechanical engineering. And then the T's, these guys are going to denote the temperature. And so we're worried about this heat transfer fluid, HTF. All right, then we've got a time scale parameter, delta, and then we've got a set of nonlinear time periods. So we're going to model this in this not very nice way during the hours or minutes we're looking at in a nonlinear fashion. So now that nice energy balance, it was just an ST is equal to ST minus 1, right? Like we're used to, like in a manufacturing facility or something. Not anymore. Every single term in blue, which is basically everything, is nonlinear. It's a bilinear term composed of 2 continuous variables. And so you can sort of see this similar tenets here. What we have in T is what we had in T minus 1 plus some stuff going in minus some stuff going out. But the thing is that this is highly nonlinear, and this is just the energy balance. Also notice we now have 2 constraints instead of 1 because we're looking at what's going on the cold side and what's going on the hot side. So then we also have a lot of other nonlinear constraints, but I would run out of time telling you about them. So just this is, a good example of how bad things really are. So let me just mention here that, on a 48-hour time horizon with the time fidelity I showed you in the timeline earlier, we've got problem instances containing thousands of variables and constraints. We do have binaries for the starts and stops. We have a lot of continuous variables as well, and the product of those continuous variables makes things quite difficult. So if we're using Gurobi, we've modeled this all in AMPL, we're getting about 10% relative optimality gaps, after 12 hours. So, this isn't going to do. You can't use this for real-time dispatch like that, right? So what are we going to do? So we did a few things, and I just wanted to highlight a couple here. There's some kind of, I would call them cuts. They're on the continuous variables, but we try to sort of tighten some things up on the continuous variables. Then we tried to discretize this mass flow rate. It's a continuous variable, and we tried to say, well, you've got to be in each unit. We're going to discretize you, and so instead of between 0 and 1, you get to be 0, 0.2, 0.4, 0.6, so forth to 1. And so that added binaries, but it also meant that we got tighter relaxations on what we had. And we also, so the second 24 hours is going to revert to our linear model. So that sort of informs us, but not at the same fidelity. But still, all we're really interested in for dispatch is, just the first 5 minutes. So we think that, an hour 30, it's okay if we're using the linear model. So this is a little bit on the cuts. You can just see it's all a function of these continuous variables plus some time scaling and some bounds on the mass flow rates. So just some differences there between the mass flow rates on the hot and cold side in different periods. Here, these were the cuts. So we went ahead and discretized that mass flow rate, and then we used an additional variable, this theta here, in order to figure out like where you are in that interval, between 0 and 1 kind of thing. And then the other thing we did is we relaxed the second half of the time horizon to be the linear part. So you can see the differences in the variables and constraints. The other thing I wanted to mention is that we had to scale the heck out of this model. So, we know that it's not very good to have differences in orders of magnitude in your data more than, let's say, 10 to the 10th, even that's not great for a linear model. But we had to be down around 10 to the 5th to get Gurobi to cooperate at all. And so there's just, the solution techniques are less developed. We're employing their spatial branch and bound because all the nonlinearities were the bilinear terms. We did have a few more binaries as evidenced by that discretization of the mass flow rate. But overall, there was a reduction in the nonlinearities, also owing to the relaxation in the second half of the time horizon and so on. And so we wound up getting better results. And I'm just going to show one here. So I have below here, the gaps averaged less than 5% with these various modifications. It depends on the initial conditions and also the pricing signal we're using. And we can get them like this after about 5 minutes of solve time. So that's a huge improvement over what we were using. So that's with AMPL and Gurobi. And if you're wondering about, well, what on earth are we doing, or how are we measuring things, or what does a solution look like? So I've got sort of a primary and a secondary axis here. And so this one on the left here, for example, this is what's going on in the receiver. So we can see receiver outlet temperature, and this is over the course of, I'll say a day-ish. But really, the reason that this day ends, before 24 hours is because the sun isn't shining for part of it. And so you can see how it's kind of ramping up. And then, of course, the temperature, the outlet temperature is, getting hotter as we're using things. And then, it decreases after you stop running the receiver in the evening. And you can also see correspondingly what the mass flow rate is doing And that's pretty much right, sitting right on top of this so-called clear sky control, which is, what we like to mimic in terms of like just how the receiver is running and how it should be run in order to, track the sun reasonably and not have too much wear and tear on the system. And then over on the power cycle side, right, so that's with the ranking cycle and so forth. Again, we have a primary and secondary axis. The green is the power purchase agreement price. So that's the price we're dealing with. So you can see a low and a high depending on the time of day. And so we're trying to sell more when the price is higher. And so you can see the cycle output. I mean, there's a little bit of things going on at the beginning, but you can essentially see over the course of a day that things are doing what you'd expect them to do, and you're generating a lot when the price is high. And then kind of when the price is lower and you're not able to generate so forth, then it's going to zero. And then the secondary axis, the hot tank temperature. And again, so the temperature in the tank is sort of increasing as we would expect as we are using the system. And so that's just a couple of performance indicators. The mechanical engineers really get into a lot of performance indicators of exactly what's going on in the system, but this is a representative sample. So that's sort of the story, the positive ending behind a little bit about the design and then more so about the dispatch. But we're very grateful that it seemed like GROWE Spatial Branch and Bound was just sort of coming into being as we were trying to get this problem solved, because I mean, we certainly had to work hard and we had to make some modifications and adjustments to our formulations. But after we did that, we were able to get something that is reasonable for the operators to adopt, which is another story unto itself. But we're almost out of time. I have a bonus section, so I'm just going to show a pretty picture or two of the bonus section, and then we can be done here. But I do want to mention that there's all kinds of problems. I mean, you could just spend your life working in concentrated solar power, and some of my colleagues do. Some of my mechanical engineering colleagues, they're looking at all kinds of things. But one very interesting operations research question, this is what Jesse Wales had worked on, is how often do you clean your mirrors? So if you don't clean them very often, what can happen is they get soiled. And so, we're in the desert here, and so the reflectivity isn't very good. And so you're not going to have very much of the sunlight you're putting onto the tower, you're transmitting to the tower. And then correspondingly, you're not going to be able to generate as much in terms of electricity. On the other hand, if you're washing them all day long, you're going to incur a lot of expense. So there's an obvious trade-off in terms of the time which you wash them. So you can see how these guys get washed. And so there are different types of vehicles. This is kind of one right there. But, some of the mirrors, depending on the facility, they're smaller and you can just like go with squeegee almost, and it's a more manual process. These mirrors are really big, as you can see. So that's some work that Jesse Wales did. He also had a nonlinear optimization model, and he developed a rather interesting decomposition heuristic in order to get this to solve quite quickly. And he was looking at what kinds of vehicles would you purchase and or deploy, and how would you deploy them in this whole concentric set of mirrors. You might assume that some of the mirrors you're going to wash more frequently if they are closer to the tower and more responsible for the amounts of light that they're able to transmit up to the tower. And indeed, we find that to be the case. So I'll just kind of skip to the end here, but you can see had a rather nice graphic. There go all our 10,053 heliostats, and you can see the different types of trucks with different efficiencies and costs associated with them, and how you would wash the concentric sets of mirrors in the field. And so that's another paper I'm happy to share if anybody's interested in looking at there. The model was a bit simpler, not as much in terms of startup and shutdown, and the nonlinearities were sort of the format where you had an exact linearization. And so, that turned out to be, it lent itself a little bit better to a, kind of a slight decomposition technique, whereas the dispatch just is grinding away as far as I'm concerned mathematically. So I think that's we're at about time. So I think I'll stop there.
Awesome. Thank you very much, Alexandra, for this very nice talk. Lots of cool applications. So in terms of questions, since we're at 2 p.m., we'll just do the breakout rooms. So folks who have questions for Professor Newman, you can join the breakout room that Alex is about to set up and ask your questions there, just in the interest of time, and the same for Professor Sefer.
Yes, and also feel free to stick around for just like the general room, just to chat.